So, in order to cover a reasonable amount of the content of this course, of the syllabus, we covered limits. We covered most of the important parts of derivatives. There's some things. I know we didn't spend as much time in lecture on exponentials and logarithms, or derivatives of exponentials and logarithms, or finding maxima and minima, partly because we've missed classes, and I expected that we would all be reading along, but so that's I know you will. So those parts you'll have to work on. And so today, what I want to cover is the other important part of the calculus course, which is integration. And if you have an understanding of derivatives, then integration is just the opposite process. So if you have a function of x, and we say the derivative takes, when you apply the derivative to f(x), then you get f prime. So we go from f to f prime by applying the derivative. No, it looks like. Huh? Is this any better? Barely. Huh? Well, let's try. I'll put it here maybe. My own. Oops. But it needs to be on the corner. Now it's a bit more dangerous, but okay, at least you can read the board. Now I just have to be really careful. We can turn it back like this. So you use the derivative. The idea of this, what I've written, is you have a function f of x. You turn it, you get the derivative of the function by applying the process we call differentiation. Okay, so you could also write here, you differentiate f to get f prime. Now suppose you want to go the other way. You have a derivative, and you want to go back to the original function. Is that possible? And the answer is yes. And that is called you integrate. And that's what we're going to learn about, is how do you go from f prime back to f. There's a few names that all mean the same thing. So when you differentiate f, what you get is called, f here is the derivative. Right? So you differentiate to get the derivative. You integrate to get, and here we can call this, one is the integral. Another name for it is the antiderivative. Antiderivative. Good morning. We just started. So you differentiate a function to get its derivative. You integrate a function to get its integral, also called the antiderivative. So the idea that you're going backwards. This is one way to think about integration. There's also another way, which I'll introduce as well. So let's start with an example. If I gave you the function x squared, let's take black. So if I have x squared, and I ask you to differentiate it, you would tell me
that is 2x.
That it's 2x. So this would become 2x. So now, if I gave you 2x, and I asked you to integrate 2x, what is the function which, when I differentiate it, gives me 2x? It's x squared. So, going back this way is reintegrate. And for powers of x, right, we had a simple kind of rule for differentiating powers of x. Remember what it is? To take the derivative, how do you get x squared to get 2x? When you differentiate.
The power of the coefficient is in as well.
So you should know the laws of the rules of derivatives by now. So if you have x to a power n, then the derivative of this is n x to the power n minus 1. Are you still with us? Are you still with us or are you lost? Not go on. Are you processing? Are you familiar when I write n, what does n mean? No? N stands for a number. So you have x to the power 2, for example. So when we write x n, anywhere, n means any number. But a constant in this case. So you could imagine n could be 1, n could be 2, 3, 4, 5, 10, 20, 100, 385. It can be negative numbers, it could be minus 1, minus 3. In fact, it can even be decimal numbers or fractions. Does that make sense when you get it? So if this is the rule for differentiating, if I give you x of n, x to the n, to the power n, and I take the derivative, then the power comes down in front and I subtract 1 from the power. So can we come up with a rule that takes us in the other direction? That's what we want. So we want a rule, I'll use the wrong color for this, but anyway, where if I give you a derivative, x to the n, what is its antiderivative? So this side, right, if we imagine here, this is the f prime side, this is the f side. Okay. Maybe that's confusing. So if I have x to the power n, differentiating it, I multiply the power in front and I subtract 1 from the power. But if I want to get the antiderivative, if x to the power n is the derivative, what is the function it came from? Can you see from there?
Yeah. Yeah.
I guess I could start again up here. But we understand the idea that integrating is the opposite process from differentiating. And those things. So now we want to know, if I have x, let's take an example. So let's say I have x cubed, and I say this is the derivative. So, in other words, let me write it over here. This is the result of d by dx of something. Do you want to sit on this side or that side?
No, it's just, I mean, it's check.
Oh. So yeah. Is it ax here? 3x. Well, let's try. If you have 3x, what is the derivative of 3x? It's 3. So this, when you take the derivative, you get 3. So that's not exactly the same thing. So let's try something else. So we know, for example, that the derivative is 1 less than the power of the thing we started with. So 3 is what you get after you subtract 1. So that means you must have started with 4. So there was an x and there was a 4. Okay, so that's a new guess. So let's try, if I differentiate x to the 4th, what does that give me? X to the 4th differentiated gives me what? 4x cubed. Okay, that's closer. I have the x cubed, that's good, but I have a 4 here that I don't have here. So, in order to end up without a 4, what do I need to add here that this 4 will not be there? Well, this is 4 times what I want, which means what I really want is a quarter of this, right? So let's put a quarter. And if I have a quarter x to the 4th, then when the 4 comes down and it divides by 4, then all I'm left with is x cubed, and that's the thing I have. So my final answer is 1/4 x to the 4th is the function whose derivative is x cubed. Okay? So now we can try to generalize. Should we do another example? Let's do another example. Let me take this off here. So we're looking for a function which, when we differentiate it, you want to suggest something? What will be the derivative? Here we had x cubed, here we could have maybe, let's do 2x squared. How about that? Simple enough? Okay. So now, we want a function which, when we differentiate it, will give us 2x squared as the derivative. So now we can, for now we're guessing until we find the right answer, and then we can see, is there a kind of a rule that can help us do this more generally.
So x to the power 3.
X to the power 3. Okay. Can you explain how? Why are we starting with x to the power 3?
Because that's the one we use when we need the derivative. It's the one that is going to give us x to the power 2.
Correct. What else would we get when we differentiate x cubed? What would be the full answer?
2x to the power.
Okay. And is that what we're looking for? Okay. So how do we get from 3x squared to 2x squared? Okay, so if we differentiate x cubed, if I have x cubed and I differentiate it, what I get is 3x squared. So how do I go from this to this? If I have something divided by 3, and what I want is something, not divided, something multiplied by 3, and I want it multiplied by 2, then I need to multiply this by what? So I don't want 3, so I need to divide by 3, basically. Right? That will cancel the 3. What would you put here now to end up with 2x squared? Two. Brilliant. So now the 3's will cancel, and what we will end up with is 2x squared. Perfect. So what we need is, if we multiply this side by 2/3, then we have to multiply this side by 2/3. And we remember from the rules of differentiation that a constant can go inside or outside the derivative. It's the same. You can move the constant in and out. Right? So the constant can go inside and we can have 2/3 x cubed. When I differentiate 2/3 x cubed, what I get is 2x squared. We're getting the idea? So right now we're basically making a guess and then adjusting the guess to arrive at the final answer. But we can look at this and realize there's a pattern. Is there a pattern to this? So one part of the pattern you've already noticed is that when you have the derivative is some power, I'm going to introduce some notation. Okay? So far we know d by dx, this means differentiation. Now we're going to introduce notation that tells us that we're doing integration. Right? So integration is done using this, looks like a very stretched S. Okay? And inside it we write the thing that is the original, the function, the 2x squared, for example, and then we write dx. Dx is not multiplying this. Dx belongs to this operator, right? Think of it like, just like this is not a division. This is not d divided by dx. This is one thing. Right? And this thing has, you feed it something. The same thing, the integral is this symbol, dx, and you feed it something in here. Okay? And then the answer is the integral. So in our case, we would write, for example, 2x squared in here, and put that in a different color actually. So we would have 2x squared, and the integral of 2x squared dx is 2/3 x cubed. And that's how we would write it. The integral of 2x squared, we don't read the dx, the dx is part of it's the integral. I guess the full, you would say the integral of 2x squared with respect to x, sometimes we say dx, it's faster than with respect to x, equals, and then the answer. The reason we have dx, we're not going to do multivariable calculus, but just like you can have a function that is a function of x, but you can have functions that have many variables, more than one variable, 2 variables, 3 variables, and you can differentiate with respect to one or more of those variables. And then similarly, you can integrate, which is the antiderivative, with respect to one or more of those variables. So the dx does matter. Sometimes you'll have a dx, dx, or dx, dy. You get double and triple integrals and so on. But we're not going to go into that. We're just going to do a simple integral. So, another thing we could write, using the examples that we have, is we would write the integral of x cubed is 1/4 x to the 4th. Right? So let's make something here, and something here. Nice. So let's see if we can come up with what is the pattern for integrals. So the integral of a function, so now we're going to write it more generally as, let me use the same. Okay. So the integral dx of x to the n will be, so when we differentiate, we subtract 1 from the power, correct? So if we integrate, we're going to do the opposite. We're going to add 1. So we're going to have x and plus 1. And then what are we going to do about the constant in front? So when we differentiate, we multiply this in front. When we integrate, what happens? If we look at our pattern, we divide by what? Yes. We divide by, and so if it's x cubed, we divide by 4. So we divide by the original power, the n plus 1. Right? So divide by n plus 1. Now, we're not quite finished. This is actually not the complete answer. We're going to see why in just a second. So at the moment, when you take the derivative of a function, so we said this equals x cubed. Right? So if I take x cubed, if I have 1/4 x to the 4th, let me just x to the 4th, 4. Suppose I add a number, I will call it c, a constant. Okay? Let's take the derivative of this. So what we're looking for is it should equal x cubed. That's the thing that we're integrating. So we said when we integrate this, we get this. So now I'm suggesting let's add a constant. This is just a number. 1, 3. What is this equal to? So that x cubed plus, so the derivative of a sum is the sum of the derivative. So we take the derivative of this, which is x cubed. The derivative of a constant is what? Zero. A constant has, the simple way to remember is graphically. So in your mind, think of, if I have a constant, the function is a constant, and I'm saying y equals a constant. What does that look like on the graph?
Y equals what?
A constant. Let's say the constant is this number here. What is the graph of this function? You guys should have this. You've done this before. Huh?
I think Y is at 0.
Y is a constant. A constant is, I just arbitrarily. Y is equal to a number. We don't know what number, but a number. So I just said, let's say the number is here. If it helps, let's say 3, right? Let's say this number is 3. Y equals 3. What is the graph of the function y equals 3? You may be thinking, but there's no x. How do I know how to...
No, x is at 0.
If there is no x here, you still think, okay, if x is 0, what is the value of y? 3. If x is 1, what is the value of y? Y is 6. Y is equal to 3. Y is equal to 3, it doesn't care what x is. X can be anything. For any value of x, y is always 3. It's a horizontal line. This is not a weird function, right? This is the function of a horizontal line, a flat line. And that's a perfectly good function, right? Is it? It is, right? Sorry, you can't really see the line here. Maybe red is better. This is, it's not very straight, but you can imagine it straight. It's better. And it could be here, there, whatever the constant is, this is the graph of that. Y equals c. I'll say this is the number c there. Now, what is the gradient of this function? It's a line. Lines have gradients, have a slope. Right? What is the slope of this line? Is it going up? No. So it can't be positive. A positive number means the slope is going up. Is it going down? No. If it was going down, a negative slope would mean you're going down. So if you're staying flat, then your slope is 0. You're not changing. So the derivative of a constant, y prime, is 0. This is how I remember when I'm not sure. A constant, I think, well, a constant is a horizontal line. A horizontal line has slope 0, so the derivative of a horizontal line, i.e. of a constant, is 0. So if you just have a constant, not multiplied by x. There's nothing of x, there's just a constant. That derivative is 0. So, what does this mean? It means that in order to get x cubed, I need the x to the 4 divided by 4. That's clear. But I can also add any number to the function. There's an infinite number of functions that all differentiate to x cubed. Because this part will always give plus 0 in the derivative. Right? Maybe the time we started or the time I was Is that the way? You see, so if I have the function x to the 4 divided by 4 plus 1, the derivative will be x cubed. If I have x to the 4 divided by 4 plus 2, the derivative is x cubed. Plus 100, minus 10, plus 1,000,000, minus 366,000. I can put any, and there's infinitely many numbers. I can put decimal numbers, right? 3.65. Any number will still give me this derivative. So the full answer is not this. The full answer is this. I didn't leave myself enough room for that. I'm going to rewrite this a little bit over, okay? So I'm just going to move this over. So x n plus 1 divided by n plus 1 plus c. And that is the full answer. This c is called the constant of integration. When you integrate, you always get this constant. And you don't know what it is. There's no way to find out. Unless I give you more information, you cannot find what is this number. You know there can be a number. And so in the general case, if I just give you, there's a function, find the integral, you will tell me plus c. And you will write plus c, where c is a constant. Cool. Now, this is called, let me write down. Already getting hot, huh? This is called an indefinite integral. So integrals come in two flavors. Indefinite. Any guesses what the other flavor is? Definite. Points for Mona. Can I erase this down here now? We got our usefulness out of it. So then the other kind is a definite integral. Sorry, these markers they're not good. I wonder if I were to Does this not write any better or worse? No, well, it doesn't help. Still recording here? Yeah. Check my notes. I think it's the integral would have to, the integral would be a better measure. Could I try to figure it out together? Okay. This one's so you can check in the textbook anyway. We're trying. Actually, no, this isn't true. Okay. There is no simple rule for products of functions in integral. There is sum and difference functions and a constant. Those are the words. Simple. How are we doing time? It's getting hard. What was time? The big breath, because it's hotter because it's. I'm getting up too. When I slept this morning, it's not going to see. Back. You slept already this morning. Not interested in. Okay, let's do a little bit with 20 minutes left. Next week will be. We can make it a review session if you like. The exam has yet to be read, but what I found is a bit of evidence, mostly about derivatives and a bit about integrals. And when I say the question is integral, we already are not give the definition of whatever rules it's here's a problem solved. So it's can you actually do problems? So you can't memorize. You have to learn the rules, but you have to know how to use them. That's it. Not true exactly. So definite integral. So the other way to interpret an integral is imagine, right? We have a curve, the old arbitrary. Depends are really not working with me anymore. Not do that anymore. I don't know what to do this. This is right. So suppose you want to know the area. And right now you say, well, why would I want to know the area of this thing? One answer may be, don't worry about it. But there's a number of applications in geometry, in physics, a lot. In economics, a bit. So one example, I think I put a question about this on here. We talked early in the semester about the concept of the marginal fund, marginal cost, marginal revenue, which was how much more do you get for each additional unit, how much does it cost to make one more unit. And it happens that if that's a function, if this is a marginal function, I don't know what we're doing here. This is if that's a marginal function, then the area, this area between the x-axis and the function, from 0 to some number, is the total cost, for example. So someone says, I don't know my total cost, I know my marginal cost function. Well, what is my total cost? And you say, I know how to do that, I take the integral. And suppose we had something like this. You would start by saying, well, how would I find the area of this? Right? It's some complicated shape. So you'd say, well, I could start by approximating here. And I could approximate it by saying, well, let's take a rectangle here. Maybe we'll make this 1 unit, some delta x. And we'll make a rectangle starting wherever the function is here. When the function is there, I make another rectangle, also delta x, and then another rectangle, and then another rectangle, another one, and another. A rectangle, we know how to get the area of rectangle, yeah? It's just the height times this. So in this case, it would be the height here is f of x dash 0, is a 0, times delta x. So this area is f of 0 delta x. Then this one is f of 1 times delta x. 1 times delta x. And so on, f of 2, f of 3, f of 4. So it's a series of values of the function times some width delta x. Now you could say, well, of course we're missing some bits, right? That's why it's an approximation. How can you make the approximation better? Well, we can make it rectangle, we can put more rectangles, make them thinner, and put more of them. Okay? So instead of delta x being 1 unit, it could be half, or a quarter, or a tenth. So then we might have this, and then this, and then this, and so on. And you see that the number we would get by adding up all of the areas of a rectangle will give you an answer that's probably closer to realism. The more rectangles we use and the thinner we make them, the better our approximation of the area. Now, this may remind you of what we did with derivatives. So remember, with derivatives we had a slope. We said if I take the line, the 2 points of the line, and I bring them closer and closer and closer together, I have delta x. And I said in the limit of delta x becoming 0. Remember that? Yeah. We're going to do something similar here. We're going to say, if I make the rectangles as tiny as possible, then the limit of that process, as I get closer and closer and closer, then I'm approaching the true value of the area of this smooth function, this continuous function, what is its area. And that's the other way of thinking of what is an integral. So the integral of x to the n, in this case, the red line, is the x to the n, which, by the way, this part here is called this x to the n is also called the integrand. It's a thing that you are integrating. So in our very first example, the integrand was, for example, the x cubed. I said, what is it that when you differentiate, you get x cubed? The x cubed was the integrand. And so we integrate, you get backward from this assumption. So this area is the area of the integrand between the x-axis and the function itself. And the function can have any shape. So the x to the n would be this, for example. That's the x to the n, suppose. Are there any other inclusions? So, the reason we want to think of it as an